everyone, and thank you so much for the warm introduction. And thanks everyone for coming early to attend my talk. And yeah, I'm going to talk about something that I think is super exciting, especially in the area of stream processing. And that is what kind of myself and my team has been working on for several years now is this new mode called real-time mode on Apache Structured Streaming, and basically allowing Apache Spark to be used in use cases that previously it was not used for. So yeah, super excited to talk about that, and thanks everyone for attending. Just a little bit about me. I've been working in mostly open source on streaming systems for most of my career. I've worked on most of the streaming systems in open source out there today at one point in my career. And now I'm at Databricks, as I mentioned, working on Spark Streaming, Structured Streaming. So this is kind of the agenda I have for my talk. I'm going to kind of provide an overview and some adoption statistics about Spark Structured Streaming. Just kind of a show of hands, how many people here know about Spark Structured Streaming or even attended kind of this keynote by my coworker Indrajit that was basically talking about some of the similar stuff? Yeah, so we have some familiarity in the room about that. Cool. But there seem to be also folks that are maybe not so familiar, so I'll go over it. The next thing, the most exciting thing I think for me is to talk about real-time mode, or we can use the acronym RTM, kind of how that works, how we extended the existing kind of Spark or structured architecture to be able to deliver millisecond latencies on the same Spark APIs that many folks already know. Next thing, talk about performance, right? That's one of the things that a lot of people look forward to for real-time mode, because the promise is delivering low latency. So we'll look at some kind of numbers and benchmarks we have run there. And lastly, I think for a lot of maybe data engineers in the room is how people have been using RTM in practice. What do we see our customers do? Some of the patterns, right, that might be interesting, that really basically let RTM kind of shine. So let me first give kind of an overview of structured streaming, or just streaming in general. So what is stream processing? I think just like the talk, the keynote, my coworker Indra described, is basically just processing streams of data. It could be from logs, right? You have VMs, generate logs, have devices, sensors, all generating data continuously, unboundedly. It's not a fixed amount of data, it's just continuous set of data. You want to apply transformations on that data, and then you want to basically power some use cases like, it could be dashboards, it could be alerting, there's many things you can think of, basically there. That's the general idea of stream processing, and typically how this kind of differentiates from something like batch processing, where you have like a fixed amount of data and you want to do it every so often, is there is a dimension of performance, which is latency. People care about latency. Different use cases in the streaming kind of area I'll talk about will have different kind of latency requirements. As you would imagine, for something like fraud detection, or something where someone is waiting in a cashier and you want to be able to do something there, see how long it takes matters. Something maybe like powering a dashboard that, okay, the freshness only needs to be like an hour, basically latency requirements can be different. So what is Spark Structured Streaming? It's just it's a distributed stream processing engine built on top of Spark SQL. You can use the same APIs you use for Spark SQL on structured streaming. I won't talk about how a lot of queries are being run on Databricks. I think if you attended the previous talk, my coworker Indrajit, he also described some of this. He also described kind of the evolution of Spark streaming a bit as well. So I won't go into that a bit, but the gist is Spark streaming, structured streaming has been around for a while, and we definitely have kind of evolved over time to be more feature complete and to be able to handle kind of more use cases. Just another recap what structured streaming is, right? If you attended the previous talk, structured streaming, we have the concept of basically these micro batches. So structured streaming, we can describe it as processing data incrementally, continuously, and basically delivering those results at the end. So you can imagine, like I mentioned before, structured streaming as basically a series of these concepts of micro batches. Each micro batch is kind of like a batch. It basically processes a fixed data range of data from, say, offset A to offset B, or from like, index A, index B, however you want to kind of describe that data range. Micro batch processes a fixed range kind of data. And there's typically kind of, this was also kind of went over in Indrajit, he's here now, slide, of kind of the life cycle of a micro batch, right? Typically, we do some sort of planning at the beginning. This is basically the query plan of the micro batch, right? And it also contains kind of the offset range of this micro batch, from what data range to what data range I want to process to, right? The reason for that is we're basically converting kind of an unbounded stream of data, right? You can't just say an unbounded stream of data to basically a bounded stream of data, these kind of micro batches to be executed incrementally and continuously to basically perform stream processing. Some of the interesting things along the way for kind of a micro batch would be obviously the planning part. There's also points where we do some sort of checkpointing and progress, persisting the progress to make sure that, once we've processed this, data range of data, we checkpoint to make sure that, okay, if there's some failures, we can basically start from the previous successfully checkpointed micro batch so that we don't have to start from the beginning. So there are basically things like that that's part of the life cycle of a single micro batch. Also previously went over, not going to go over in detail, but we've seen tremendous adoption of basically structured streaming jobs at Databricks. We see over 60% year-over-year growth, which also kind of gives at least, a person like me, which I've been in stream processing for a while, like it really excites me because that tells me that, wow, there's people now that's actually, starting to pay attention to to basically streaming. And people are actually using it, because back in the day, when I was in grad school working on this kind of stuff, my advisor would say, streaming is the next big thing, it's in the future, but we're working on things in the future. And maybe not now, there's now usage, but it's in the future. But I think we're finally to a point where people are really taking this seriously and really committing resources, just like Databricks, to basically develop their kind of streaming or stream processing strategy. So let me kind of go over some of the reasons why I think structured streaming has been successful. I've worked on a lot of the peer systems like Storm and Flink before, but why do I think structured streaming is successful? It's one of the key reasons, I think, there's a low barrier to entry. A lot of people are already using Spark for doing various things. You can very easily create a streaming application using the same API, same engine, same environment, and basically now you've created, a streaming pipeline. So that's, I think, hello? Oh. One of the key reasons I think, structured streaming or Spark streaming has, one of the reasons it has become popular or, have a lot of usage. The next thing is compatibility with the Spark ecosystem, like I mentioned, same APIs, same kind of data frame model, same optimizations, low barrier to entry. And in terms of latency, for, a lot of the streaming use cases, especially in the area of ETL, right? Extract, transform, and load. A lot of these use cases, the latency that structured streaming was able to deliver was good enough, right? A lot of the use cases, honestly, did not require basically sub-second latencies, or even a lot of times sub-minute latencies. People just cared about simplicity of usage, simplicity of management, and minute latencies or even tens of seconds of latencies was good enough. So that current micro batch architecture that exists today in structured streaming was good enough for, a vast majority of these kind of ETL use cases or ingestion use cases that users have been, using structured streaming for. But I think there has been some evolution of industry requirements. I think more and more users are looking to use engines or tools available that require lower latency. You can think about the areas of fraud detection, feature serving, personalization, IoT. So definitely seeing the emergence of basically users wanting to not use their own or manage their own kind of proprietary implementation of these kind of workflows, but rather use already kind of systems out there to basically power them. So they don't have to do the maintenance and support of that, and they want to, like many data engineers do, they just want to focus on that business logic and want to basically leave the management or details of running an engine or platform to basically someone else, right? And the key here, like what I mentioned, is microbatch was designed for seconds to minutes of latency, and millisecond latencies for this kind of microbatch architecture was kind of out of reach. So this is kind of one of the reasons why we developed real-time mode, is to basically address this kind of this area. So let me kind of give you maybe a little context. I'll go over this real quick of why microbatch cannot hit millisecond latencies. A lot of it is kind of within the overheads of actually running a microbatch. As I mentioned, there's a lot of steps within kind of a microbatch that's not just processing the data. It's like doing query planning, it's persisting offsets, persisting state, all of those things. There's a lot of overheads per kind of per batch, so that contributes to kind of microbatch. You can't actually make it too small because then all these kind of overheads dominate the execution time of the microbatch, and then you can't really get a lot of good throughput or sustain any sort of throughput. So a lot of these things contribute to kind of the inefficiencies if you actually want to shrink a microbatch to be smaller in an effort to basically deliver lower latency. Another kind of interesting point is kind of I want to illustrate here is kind of how the engine works, right? Typically, like I mentioned before, is we would plan a microbatch from basically offset A to offset B, and then we would basically process the data within that data range. So what inevitably happens is when you're actually, if you think about it, the data you're processing currently is actually data that's been buffering in maybe Kafka or somewhere else, when we're processing the data of the previous microbatch. So there is inevitably kind of a delay that occurs in this kind of microbatch architecture, which again could be fine for a lot of use cases, but definitely it makes it difficult to get really low millisecond P99 latencies. Some other kind of limitations here and there about stragglers and sequential stage execution. That's one of the things as well as in the current microbatch model, stages are executed one at a time. After, if you have a kind of a map reduce type of workload, let's say the map stage executes, all of the tasks in that stage finish, and then the reduce stage, executes, and we're using kind of blocking shuffles to basically implement that. That's also an area where latency can be introduced. Another interesting point I want to bring up is kind of the idea of platform fragmentation, right? I think in the previous talk by my coworker, Indrajit described a similar situation where for a lot of these ETL cases, batch cases, Spark is already used very heavily. But for these use cases where you have lower latency, right? You need millisecond latencies. Maybe something like Apache Flink or previously Apache Storm is used, and engineering teams or platform teams have to now manage kind of both, right? And there's comes with operational complexity. Now engineers or data engineers need to know the API of both and the intricacies of both, and that creates additional burden from basically for engineers all across the stack to have to deal with kind of two engines. And for a long time, that's kind of how engineering teams and data engineers had to deal with. So now let me kind of introduce real-time mode, right? And how kind of real-time mode can help alleviate some of these kind of issues and deliver lower latency. So this is kind of where we see real-time mode in the terms of the latencies it can deliver and the type of use cases that it is used to power. So for microbatch kind of mode is what we call kind of the existing kind of architecture in structured streaming. is we're targeting, basically use cases are like streaming ingestion, ETL, like I mentioned, that are in the seconds or more kind of latency range. For real-time mode, RTM, we're targeting these operational use cases, right? Like fraud detection, sensor monitoring, that really require latencies, say under a second, or really in the low hundreds of milliseconds, if not, in the tens of milliseconds or single-digit milliseconds. And that's what kind of we were building real-time mode to latencies to target the use cases that exist in those and for those latency ranges. Oh, sorry. So let me now talk about kind of the architecture and how we extended the existing Spark Structured Streaming architecture to be able to kind of deliver those kind of latencies. So let me just go over the big ideas, right? One is, like I mentioned before, microbatches are basically executing data for, a fixed data range, right? From A to B. Now we've kind of reimagined microbatches. Instead of basically executing data for a fixed data range, now we're going to just run them for a fixed amount of time. It's kind of a difference. So we're kind of involving this idea of checkpointing every amount of data that we process to checkpointing the data we processed for a fixed amount of time. So this basically allows us to do continuous kind of processing of the data. And the other thing we wanted that the high-level idea that we did is run stages concurrently. So no longer are we basically in this kind of blocking architecture where you run one stage and then you run the next stage and so on and so forth. Now all stages run concurrently. So data basically flows through basically upstream to downstream. Whenever it's ready to be processed downstream, it'll just send it directly downstream to be processed. So this is kind of the evolution of that architecture. Instead of processing data that's basically buffering when the previous microbatch was being executed, now we're just basically continuously pulling fresh data from the source to be processed. And the other thing is we've re-implemented kind of a shuffle here. Instead of the disk-based sort kind of shuffle that exists in Spark, we implemented a new shuffle, a streaming shuffle, a pipeline shuffle, in which it's there to connect all of the stages that are running concurrently. Once some sort of output is available to be, is already processed and ready to be sent downstream, it is sent immediately instead of being basically buffered somewhere and waiting for the current stage to be completed, and then for the next stage, basically pull those buffers to continue the processing. So everything, all the data processing now is basically pipelined, and that really, reduces kind of the latency you're able to get for your data. Okay. So there's some other kind of optimizations we had to do because there were some assumptions like operators were buffering data for a long time because it was a fixed data range. So we had to change some of those things in Spark and how operators and some of the operator implementations to make it more streamlined and row-to-row processing instead of assuming kind of the whole data kind of is available. So we've done those optimizations, also incremental state cleanup to make sure that we're not just cleaning up all at the end of a batch, but also incrementally. Those are kind of details I won't go too much into, but in general, I think the takeaway for especially a data engineering crowd is, we've extended the existing microbatch architecture and structured streaming. We've extended a way that now we have time-based kind of microbatches, and now you can think about them as more of like checkpoint intervals, right? We've moved away from just checkpointing based on data range, now time-based basically checkpointing, and now all stages run concurrently, so data is processed in an extremely pipelined fashion. And this is one of, I think, in the previous talk we went over this, but one of the kind of most exciting things for me and for kind of the design for RTM is that you can seamlessly kind of switch to using real-time mode for your existing structured streaming queries. You don't have to rewrite, basically. If you already have a structured streaming query, right, structured streaming application, you can simply change just one line of code, right, to use basically this real-time mode trigger And you should be able to see orders of magnitudes improvement in your latency. So that's one of the, I think, coolest things about this is, we're not asking you to rewrite your application. We're not asking you to use a different API. Same API. You just have to basically indicate that, yes, I want to use this new kind of mode to execute my query. Let me talk about kind of the semantics of real-time mode and what it delivers. So for fault handling in terms of like processing guarantees, it's exactly the same as micro batch mode, the existing mode. Just like in the previous talk, there's an exactly once basically processing guarantee that each record affects state managed by the engine exactly once. So that doesn't change. That guarantee, does not change. For the end-to-end guarantees, for now, kind of real-time mode is targeting these applications that require lower latency, such as writing to Kafka, OLTP, or some sort of custom sync. That is at least once. So a lot of the times, and this is also from kind of experience from previous work, that at least once for these lower latency use cases is good enough. If you do want to do exactly once, there are ways to do it, but that often comes with a trade-off of latency. So for the processing side, we have exactly once processing. For the delivery side, there can be kind of duplicates, so that's something to be aware of. And for the performance, this is some benchmarks we've run for a list of kind of interesting use cases that we commonly see users use for these low latency use cases, comparing basically real-time mode to the baseline here, which is the existing kind of vanilla micro batch mode. And for a lot of these use cases, you can see this graph displays the P99 latency. There's over an order of magnitude improvement for latency. No longer are you basically dealing with second, or multi-second, or tens of seconds of latency. Now you're basically dealing with latencies in the milliseconds, not hundreds of milliseconds. I think in the previous talk we already shared the slide. There's also a blog that we published recently at Databricks comparing it with Flink with some of the kind of key kind of benchmarks that we've ran. It's fairly competitive with Flink on a lot of these workloads, and even better in some cases. So I think one of the things I wanted to talk about and spend some time is kind of the case studies, right? Like, where do we see real-time mode really being used, and where do we see real-time mode kind of really shine? One of the use cases is real-time feature engineering for things like fraud detection. But you can, I have an example here, fraud detection, but it's really kind of feature engineering in general, right? But let's take, for example, this hypothetical scenario of fraud detection. What is the context? Let's say I am a bank or a financial institution, and I, process transactions, could be credit card transactions, and I want to use basically ML to, flag or detect, suspicious or potentially fraudulent transactions, right? That is a use case. Some of the features that go into, say, examples of features that go into basically this pipeline could be something like the number of transactions in the last some window of time, let's say hour, some sort of merchant risk score, or geolocation anomalies. Usually this kind of data that's grouped in, by some sort of, or scoped to some sort of window of time, right? And there's typically two kind of different flows that, or workflows that go into kind of feature engineering. One is the training workflow, right? Where I'm actually training my model. This is where I'm using kind of historical data that I have that I'm logged somewhere, computing these features over some period of time. And then I also have the expected results. And from that, I am basically training my model to match the features were at that point in time to the expected results, right? So that is kind of you don't really have any sort of time sensitivity there. You can do that kind of at your own convenience. But there is also another path, is basically the online serving path, where you actually are getting live transactions. You're computing maybe these features, right, dynamically or live, and then you're using that model to make a decision on based off the features, like, is this a fraudulent transaction or not? This is the flow where latency really matters, because any sort of delay could mean that fraudulent transactions go through, or users have to wait longer, right? And one of the key things here is computation of these features, right? In the past, Spark has been used to compute for the offline kind of training model, these kind of features for that query, for that workflow. But for the online part, maybe some other engine is used because structured streaming Spark cannot support those kind of latencies. But one of the things that's very important to know is it's very important that the way you compute these features for your offline and your online, basically feature store or serving, has to be the same. If there's any sort of deviation, right, then you basically get this concept of training serving skew, and your results from your inference may not be very high quality. Here I have some more basically details about offline feature store. Some of the things is, like I mentioned, you would basically load historical data, do these things called point-in-time correct lookups of, at this point in time, what are the values for my features, right? I would do that computation. What are my expected results, right? Were they actually fraudulent or are they not, right? And then I train my model based off of kind of that. Again, latency not sensitive. And for the online part, I have now live transactions coming in from real users. I need to basically compute the same features, let's say X number of transactions for this window, and I want to be able to compute these features with very low latency, because when I'm doing my kind of training my model, I'm looking up at this exact point in time, these are my features, and my model basically should produce the expected result, right? So for the online path, I'm having to compute these features, hopefully with very low latency, and then write them into my online store, and then for my model, basically use the incoming transactions as well as the features to basically make the decision of whether it's fraudulent or not. This is where we need latency in the milliseconds, and also we need basically consistency of either how you computed those features, right? Be consistent with how they're computed and your kind of when you're doing your model training. This is where we see a lot of customers and users really like real-time mode, because like I before, they have this platform fragmentation kind of issue. You have to deal with Spark on one end and then deal with another engine like Fling, Kafka Streams, or Storm, whatever you want to use there, for your kind of online part. And now, basically with real-time mode, you can consolidate that architecture on Spark. You can use both for your offline workflows, you can basically use Spark. And this, I think, a lot of feedback from customers is really helps them in terms of minimizing any sort of risk that they have in training serving skew, in terms of engineers accidentally introducing nuances or differences between how they're computing the features and their offline workflow and how they're computing the features and their online workflow. Also, obviously, it reduces operational burden, and engineers, data engineers, just need to kind of be familiar with kind of one engine instead of multiple ones. So that's kind of one kind of area where we've seen a lot of folks really appreciate that we've created this real-time mode. And another interesting kind of case study, I think, still in the same area of feature engineering, is we had some customers or just users that were already using Spark or Databricks for both training and serving. They did this because they were not willing to run a different platform for many reasons, like had to run another engine. So they were just taking latency hit in terms of on their basically online serving path, that their freshness of their features are delayed potentially by seconds, if not minutes. So interestingly enough, this is also an area that causes training serving skew. Yeah, better? How people are training their models is, like I mentioned, during these point-in-time correct lookups, right? At this point in time, what are the values for my features? These are the expected kind of results. Train my model based off of that. That's basically no latency, right? This is the current data at this current point in time, right? And this is the results. With latency, when you're computing these features, that creates time skew, right? That no longer that the features are fresh. They're basically this current time plus, this number of seconds or this number of minutes, which also creates basically this kind of skew that impacts model inference performance. So just these customers simply, after we reintroduce real-time mode, they simply, sounds good. So they simply just enabled real-time mode, and they got much lower latency, and they were actually able to see much better inference results just due to that. Just because their features are much more fresh, that they're able to basically get higher quality, results. That's kind of most of my talk, but I just wanted to also mention that, just like I think mentioned before, in Spark 4.1, where Databricks were releasing kind of a lot of features, that we open source a lot of features, and one of them is real-time mode. Currently in 4.1, we are basically open sourced stateless support for real-time mode, but we're looking also to open source more for real-time mode to extend that to stateful queries, so on and so forth. So I would encourage everyone to try it out for yourself and Apache Spark, and also stay tuned for basically more features we'll open source for real-time mode. Join the community, help us work on Spark. Would love your feedback.